Yeah, hi everybody. So I'm Alistair Logan. I work for the Canal River Trust. I've been involved on the Toddbrook project since 2019, so pretty much from the day of the incident. So I'm going to take you through the background and the constraints and key stakeholders of the project, and then I'm going to hand over to Abby Morgan, who is going to take us through optioneering and public consultation, EIA and planning, and then finally over to Anthea, who is going to take us through the detailed design process, and then lastly back to me just to sort of take you through some of the pictures of the current progress of the project on site. So next one, please, Anthea. So the dam at Toddbrook Reservoir was constructed following Act of Parliament for the formation of the Peak Forest Canal in 1794. Now, the dam didn't start construction until 1837 through to 1840, and it's actually the third dam at the site. The first was located about 120 metres upstream, but due to difficult ground conditions, they looked for an alternative site. Again, water issues at the second site resulted in the current construction location. So the reservoir holds a volume of 1.23 million metres cubed of water. So put that in a bit more of a visual context, that's 7.7 million bathtubs. I sort of went and sort of roughly looked up. And it's an earth embankment dam of the Pennine type, sort of pretty typical for a 19th century dam. It's got a crest length of 310 metres long, and it's about 24 metres high at its highest. We're quite lucky within our archives to hold some of the original construction drawings from the time, and even sort of meeting minutes through the construction process, which has been quite useful as background information for this project. So on to the next one, Anthea. So this is just a quick slide of what the area looked like prior to the construction of the dam. So it shows the natural alignment of the Toddbrook running through site, which is quite interesting to see with the reservoir empty. It's now quite an obvious feature in the bottom of the reservoir there. I've just marked up, just to give you an understanding of where the dam location is. Green on the right hand side, that's the present construction. The blue line in the middle, that was where they sort of initially tried building the first dam, and then the purple line at the end is the second location they tried, where they found very porous bedrocks, so they had sort of a lot of leakage issues in that location. Right, next one, please, Anthea. So this is the dam sort of circa 1969, and a large storm event in 1964 sort of resulted in the current primary spillway overtopping by a level of circa 1 metre, which was the key sort of prompt for the design and construction of the current auxiliary spillway, which failed during the event in August 2019. So click onto the next slide, Abby, please. So this is the current auxiliary spillway in construction circa 1970. So relatively quick construction of this. It was designed completed 1969, with full construction happening throughout the year of 1970 and completed 1971. Right, next slide, please. So as most of you are probably aware, there was a rainfall event on the 30th and 31st of July, which was a 1 in 40 followed by a 1 in 50 year event. This resulted in approximately a 1 in 90 year rain sort of outflow event from the reservoir, which resulted in activation of the auxiliary spillway. Following this event, or during the event, there was failure of the upper spillway chute. This happened on the 1st of August, which prompted the Trust to initiate its emergency drawdown procedure. It was declared a national incident, which resulted in us seeking assistance from the RAF, which you can see obviously the Chinook there dropping in bags, which were brought in to help stabilise the dam face over concerns of instability due to the water level within the reservoir. Following the incident, an emergency S10 report, emergency S10 was called, which was undertaken in October. And as well as this, 2 independent reviews were commissioned. So there was the DEFRA commissioned report led by Professor Barnforth, the former president of the Institute of Civil Engineers. And as well as this, the Trust commissioned its own report into the incident, both of which, for those of you interested in the background of the failure mechanism of the spillway, are available online. Next slide, please, Abby. Sorry, Anthea. So as part of the emergency response, as I mentioned, an emergency S10 was called. The Trust implemented a water management plan, which was formulated in agreement with the Environment Agency and the QC appointed to the project, Martin Hewitt. As well as this, we undertook some emergency repairs to the auxiliary spillway, which involved creating a downstand sort of nib which extends into the top of the clay core, prevent sort of further seepage in under the auxiliary spillway slab. This crest block, which you can see in the picture on the right hand side, and combined with the emergency water management plan, which results in operating the reservoir at 12 metres below top water level. This now gives the downstream population of Whaley Bridge a 1 in 10,000 year standard of protection while we sort of undertake the works. As part of this water management plan, one of the key constraints is we have to pass, allow 2.5 metres cubed per second of water to pass around the bypass channel at all times. So I go to the next slide, please, quickly. So yeah, so just some key dates before I move on to sort of a general orientation of the reservoir. So yeah, just to recap, the incident happened on the 1st of August 2019. This was then followed by an emergency S10 inspection in October 2019. The S10 report was finalised and agreed in March 2020. And following this, the Trust produced basically a brief for the works required and went out to competitive tender, and on the back of this, Arup were appointed as the design consultant for the works in July 2020, and we have the final completion date of March 2024. So next slide, please, Anthea. So this is a view of Toddbrook Reservoir not long after the incident. We still had sort of on the plan, you can see we're moving the pumps over from the right hand side, you can see on the screen, over to the left hand side. So if you click once, I'm hoping the next one comes up. So yes, as mentioned, we're quite fortunate at Toddbrook Reservoir that there is actually a bypass channel from the inlet structure which runs the whole way round the reservoir past the auxiliary spillway. Next click. So there's 2 inlets to the reservoir. There's a large one at the top end of the reservoir, which effectively any flows beyond sort of a small bypass flow of 2.5 metres cubed per second come into the reservoir. There's our formal abstraction point, which is the second red arrow partway down from the top of the screen. Next click, please. There are 2 low-level outlets from the reservoir which provide our feeder to the canal. So currently these are no inlet control pipes that run through the reservoir, so our only control on those pipes are at the downstream tunnels that you can see. So we've got a slightly higher level and a low level draw off, which provide our supply to the canal. Next one, yeah. There is then the auxiliary spillway, which is highlighted there in green. And next click. Auxiliary spillway, sorry, primary spillway, auxiliary spillway. Next one, please, Anthea. Knew I shouldn't have put so many clicks on this. There is the dotted line just added is an existing feature within the reservoir from the predates the reservoir from the original water abstraction point. There used to just be a bifurcation structure in the Toddbrook. Next click, please. So that's sort of the orientation of the reservoir. So the main constraints at the reservoir, the primary one really is a lot of the physical constraints. It's located within the town of Whaley Bridge. The access to site is up a very narrow lane to Toddbrook, up Reservoir Road, sorry, to Toddbrook Reservoir. There's a railway line that runs through the centre of town with low bridges and access which constrains site access. There's housing in close proximity. I don't know if you can see on the map where it says canal feeders, the 2 pointers. There's actually a new housing development which has gone in on the left-hand toe of the dam. There's existing sort of properties such as Toddbrook Lodge, which actually sit within the primary spillway, and also Whaley Bridge Sailing Club. There's also a number of environmental and ecological constraints. Toddbrook Reservoir forms a triple SI for the presence of bryophytes, which are primarily at the top end of the reservoir, but we actually have, in terms of our normal day-to-day operation, requirement to draw the reservoir a certain amount down each year to ensure that good habitat is maintained for those. We obviously have water management constraints on the site. So as I mentioned before, the bypass channel which runs around the reservoir, one of our MIOS measures from the S10 report is that throughout the works we need to maintain a capacity of 2.5 meters cubed per second in that channel, which brings in a number of sort of construction constraints that need to be built into the water management plan. There's also trust operations. This is a key water supply for the Canal River Trust to our hydrological unit of the Peak Forest and Macclesfield canals. We have 4 reservoirs that feed into that area, and Toddbrook provides 34% of our water supply. So the last 2 boating seasons throughout the summertime, we have had to operate restrictions where we've had to close the canal for navigation. So it is a critical piece of infrastructure for us in terms of our day-to-day operation. Planning, obviously it's a well-known site with, I suppose, a bit of a political element, and given its location, it's very much in the public knowledge. It sits within a park that's well used within Whaley Bridge. So planning was a key concern of the trust in terms of making sure that we were going to get through planning as smoothly as possible. And as I mentioned, yeah, access and buildability, the site is heavily constrained, both for access and in terms of topography, steep slopes on all sides with poor ground conditions. And land ownership, the trust own effectively all the way up to the toe of the dam, but as soon as we're out of the footprint of the dam, so basically the line along the existing primary spillway, once we're outside of that, we're onto High Peak Borough Council land, which has left us sort of very constrained in terms of where we can put the dam. So we've had to work very closely with our sort of partners in both High Peak Borough Council and other organisations to ensure we can build this project. And then the site is crisscrossed by a number of public rights of way. Next one, please, Anthea, which I think is my last slide. Yeah, so some of the key stakeholders, obviously local residents, including those on Reservoir Road and Park Road, where our 2 main site accesses are. Obviously, during the incident, we had to evacuate more than 1,000 people out of their homes. So local residents have been key stakeholders for us because we've been wanting to ensure that they are happy and confident that we are doing our due diligence and that they're confident to live in Whaley Bridge with our assets in close proximity to them. High Peak Borough Council, as I mentioned, they own the land immediately downstream, which is the park. They're also the local planning authority, and they've obviously it's a well-used area, their parkland, so working along with them, their chief exec, their local resilience forum, making sure that they were fully abreast of what we were doing the whole way through the project was a key part for us, just to ensure that we got as much feedback from them that we could incorporate into the scheme as possible to make things as smooth as possible. Toddbrook Sailing Club, their sailing club is effectively on right at the toe of the dam, right where our current proposal has gone. So we've had to work closely with the sailing club to make sure that we minimise the impact to them and taken into their considerations around their operation. The Memorial Park Group, it was an award-winning park, and again, key concerns for them, obviously, are they going to get the park back in a better condition? Town councillors, the local MP, politically a bit of a hot potato, so there's been a lot of sort of stakeholder liaison that's had to go on between both the town councillors and the MP. The Environment Agency, both in terms of reservoir safety, water quality, and also a key one for us, downstream flood risk and how the impact of the scheme would be on that, particularly across the whole flow range, which I know Anthony is going to come on to a bit later on, as that was one of the sort of key constraints on the design as we were working through. And Natural England, obviously, as I mentioned, it's a SSSI, so obviously everything we've been doing, particularly around temporary works and access in and out of the reservoir, and also how long we've been keeping the reservoir empty. Toddbrook Lodge, as I mentioned, is within the site, so we've had key stakeholders there. And also the wider community. The reservoir was not only used for sailing and wild swimming, but it was a popular beach area that used to form every year, so it's quite a popular location with the wider community as a whole, as a resource. And then finally, the Canal River Trust. We have a lot of our own internal stakeholders, from ecologists, heritage advisors, who are keen, not for us to basically go ripping out any of the historical infrastructure without it being properly recorded, or where we can, incorporating it into the new design. So that's effectively a bit of a background of the project and where we're up to, and then I will hand it over to the experts who will take it from here. So Abby, over to you.
Thanks, Alistair. Right, I'm going to talk to you a little bit about the optioneering process that we went through relating to the spillway works, and also planning an environmental impact assessment and stakeholder engagement. So as Alex explained, we were appointed in July 2020, and we're on quite a tight time scale. So our first task was to get on with some optioneering, to work out the best way to provide sufficient overflow capacity. And this was to meet the recommendations from the Section 10 inspection report that had been carried out. So we had to safely and reliably be able to pass the safety check flood, which in this case is the probable maximum flood, which we estimated at the optioneering time was about 185 cumex. The optioneering process is kind of illustrated at the top of the slide there. We went through an options identification stage, carried out assessment of those options, and then we reviewed that in an options workshop. The bottom of the slide there illustrates the key parties within the wider project teams, as well as the Canal River Trust as our client, ourselves as designer. Kia were appointed to the Canal River Trust as their framework contractor to be constructing our design. So it was important for us to get their input throughout the project. So they've been involved. And then I think Alistair touched on the QCE, the Qualified Civil Engineer, who was appointed to sort of oversee the project from a Reservoirs Act perspective. Martin Hewitt is an All Reservoirs Panel Engineer from Mott MacDonald, and he has been overseeing the whole process. So we worked together as the project team to sort of carry out that options workshop, and then worked forwards to come up with the preferred option. So it's as Arup's design team, we sort of went away at the start and got all the information that we could collect from the trust, and we sort of augmented that with some surveys, some initial phase 1 habitat surveys, some initial geotechnical investigations to try and understand the constraints better. We came up with 13 options for how we could improve the spillway capacity, and these varied quite widely, from the extreme options of discontinuing or effectively getting rid of the dam, or rebuilding it, to sort of a lot the other end of the scale. We had sort of repairing the existing auxiliary spillway and primary spillway, and then we had sort of the middle ground options of siting a new spillway which would replace the existing primary and auxiliary spillway. And that new spillway, we looked at various different options for locating that, taking on board all the constraints that we had. So before the options workshop, Arup assessed those 13 options against the assessment criteria that we've got listed on the screen there. And Keir were really helpful by providing input at this stage there, to give us some estimated construction costs, and also to help us assess the construction access and buildability for the different options. So the outcome of our first options workshop was that we had a short list of 2 options that we looked at in more detail. Next slide, please, Anthea. So this slide illustrates the 2 shortlisted options that we came up with. On the left, we have option A, which is a new spillway situated on the left-hand side of the dam as we're looking downstream. And this would be incorporating what's called a bathtub weir. There's a photograph at the bottom that illustrates what that would look like from another dam. And that the water will flow over that bathtub weir, down a spillway channel, through the park and connect into the River Goyt, downstream of where the existing spillway connects into the river. And the other option, option B, is on the right of the screen, and that is a tumble bay type weir, which is illustrated at the bottom. There's I think that's one of Yorkshire Water's dams, to show what that would look like. And that's the flow would go over that over that side channel weir into the tumble bay and down a spillway channel, which would go through the Memorial Park woodland, quite a steep option, and then that would connect into the River Goyt upstream of where the existing connection is. Next slide, please. So as part of the assessment of those 2 options, the further assessment to try and come up with a preferred solution, we did some initial public consultation. As Alistair explained, there's a lot of key stakeholders associated with the project, and the Trust have been really keen and very good at keeping the public informed throughout the process of even following the incident. They had a community liaison officer, and they've got a website they keep up to date. They've done letter drops, site visits, and pop-up events. And so they were very keen to keep the public up to date with the optioneering process. So we did our first public consultation during September 2020 to get the public's view on those 2 shortlisted options that we've just shown. This was during COVID. So I think it was just after the first wave. So we were able to do a socially distant public events. The bottom photo there on the right-hand side shows the Trust transshipment warehouse, which is quite spacious. So we were able to do public events within that space. And we also use Arup's virtual engage tool, which there's a screenshot from on the bottom left-hand side of the slide. And this effectively allows people to access the consultation material online, and they can effectively walk through the consultation room, look at all the materials, and then they can leave their feedback online, and we can use that and review that. But it was really useful to do that public consultation at that stage. It did help us to see which option the public preferred. There was a slight preference for option A, but there was also a lot of concerns raised by the public, in particular on the environment, visual impact, the impact on the park, potential downstream flooding, and they were also very concerned about the disruption due to construction during the construction of the project. But it was really good that we could note all those concerns, and then that could feed that into our design going forwards. Next slide, please. So the further evaluation of the shortlisted options, as I've explained, we did public consultation. We also did further ecology and environmental surveys, including bat activity surveys, to try and understand the impacts from an environmental perspective. We did work to further develop the alignment of the two options to try and avoid the physical constraints that Alistair mentioned earlier. We had more detailed topographical surveys done of the two ends of the dams that would allow us to accurately locate some of the underground assets like the canal feeders, and also some of the above ground assets. And alongside developing the alignment, we were developing high level hydraulic design, so sizing the weir length, the overflow channel width and depth and gradients, and the stilling basin that we'd need at the end of the channel to reduce the energy. So sizing those for the two different options to try and avoid all the physical constraints. Obviously, we had the need to consider health and safety hazards during our design to try and avoid and minimise the risks over the life cycle of the project, and in particular making sure that we provide safe access to the structures for operation and maintenance, which Anthea will talk about a bit more detail later. We looked at the flood risk of the two options. We did some initial high-level assessment relating to the discharge position of the two options. We were able to get some flood maps and model results from the Environment Agency to help us to review that. And we consider that because option B, the right-hand side option, discharged upstream of the existing discharge from the reservoir spillway, that it was potential a problem that we may increase flood levels in the River Goyt. So that was obviously a key consideration for that option. We also did additional ground investigation. The photograph here illustrates that it was actually quite difficult to do that site investigation on the downstream face of the dam, which is very steep. But that helped us to better understand the ground risks and the groundwater risk for both of the options, including risks such as historical landslips and high groundwater. And we're also keen to try and minimise the landscape and visual impact of the options. So we were working to try and minimise those. Next slide, please. So following that evaluation that we'd done of those options, and we had another workshop with the wider project team, and we kind of reviewed the information that we'd prepared. And I should explain as well that Keir, I've just talked about the work that Arup had done there to better understand the options, but Keir had also done work to better understand access and constructability constraints. So what's illustrated here is our proposed scheme, which is the outcome of the optioneering, which is effectively a slightly revised version of option A. So this will allow the existing primary and auxiliary spillways to be abandoned and effectively not used anymore, and replaced with a new spillway at the left-hand end. It's a side channel weir spillways. We moved away from the bathtub option, and Anthea will talk about this in a bit more detail later, but just to explain that this sort of illustrates the basic concept. So the water will go over the weir, down the spillway chute, and then it will go through a channel and end up in the River Goyt. The channel runs through the parkland at the bottom, so we were keen to start working with our landscape architects to see how we can sort of optimize that channel and try and integrate that into the parkland. So these materials that we're showing here were prepared to be able to, for the Trust to be able to use as part of a public announcement, which they did in March 2021, again, trying to keep the public informed of our optioneering progress. So we presented this sort of simplified schematic to help try and explain the scheme. And also on the right-hand side, we had some sort of artist impressions sketched up by our landscape team to try and show people what it might look like, to hopefully make it easier to understand. A key decision that we made at this stage when selecting this proposed option was essentially the Trust accepted that the option that we presented here would unfortunately require the relocation of the sailing club buildings and facilities. And I think it's quite a difficult decision to make, but it really enabled us to optimize this design and come up with this design here, which has allowed the spillway chute to be sort of nestled into the existing landscape to try and reduce the visual impact. So yeah, next slide, please, Anthea. So yeah, we, as I said, we've had to relocate not only the sailing club building, but the slipway, the clubhouse, and the boat house facilities. And this is a sort of another part of the project that Arup were able to help the Trust with. So we carried out an initial feasibility study to look at options for relocation of the different facilities. And then we appointed Group Ginger architects to help us with the consultation process and also develop options for the buildings. And some of the material that we've shown here is from the planning application and the consultation work that we carried out. So we effectively set this up as a separate project led by our Arup Buildings team, who are a lot more used to the building type projects supported by our highways and landscape architects. But obviously we kept a close integration with the main project team to sort of integrate the two designs. Next slide, please. So now we've got our preferred solution. Obviously we were carrying on with the outline design and then detailed design, which again Anthony will talk about later. But at this stage we carried out some further consultation and stakeholder engagement. In June 2021, the Trust carried out a lot of stakeholder engagement with the people that Alistair had highlighted earlier, with key stakeholders such as the High Peak Borough Council Parks Department to talk about how we were going to relocate playground facilities. The Trust consulted on the plans for the sailing club relocation options and had a lot of consultation with the sailing club and the local residents. And our landscape team started developing proposals for the parkland and how the spillway could be integrated into the parkland, which is what is illustrated here. And we did our second public consultation, and part of that was consulting the public on what they'd like to see in the parkland, what would they like to see in the park, and we were able to use the information that we gathered in that second public consultation to help shape our designs going forward. Next, please. So as Alistair explained, we had to get planning permission for the project, and the planning process was led by the Trust's National Planning Manager, and the application submitted to High Peak Borough Council we got some pre-application advice before submitting the planning application and supporting EIA in November 2021. Arup were able to support by providing various deliverables to support that application, listed out a few here. And these are all done based on our sort of outline design. Illustrated there is one of the figures from the biodiversity net gain assessment, which we carried out using landscape design to be able to demonstrate a 15% net gain as a result of the scheme, using a mixture of on-site and off-site planting. What else have we got on that list? So yeah, we were also able to help with the statement of community involvement, being able to summarise the different engagement and public consultation, and how we develop the design, you know, based on the feedback that we got on those. And the Sailing Club design, there was quite a lot of work associated with that as well. Next, please. So the planning application was supported by an environmental impact assessment. We submitted a scoping opinion and effectively screened out quite a lot of topics, but these were the chapters that we ended up preparing as part of the environmental impact assessment. There's a few figures there. I think we've got any ecological constraints there in the top right hand corner. There's one of the visualizations from the visual impact assessment there, and obviously, as Alistair explained, there's a few key sort of heritage items which were important to consider with the cultural heritage. Next slide, please. So I won't go into a lot of detail. I'm not going to pretend I understand a lot about the environmental impact assessment, but we did sort of summarize, in summary, the significant residual effects were largely to do with the construction phase, visual impact, noise and vibration due to the proposed works. For the operational phase, in terms of visual impact, there were a couple of viewpoints which were considered to experience moderate adverse significant effects. But there was one viewpoint which is illustrated here, which was considered to experience moderate beneficial effects due to us grassing over the existing concrete auxiliary spillway. So the top picture shows that spillway in position, and the bottom one, although you can see our new spillway is encroaching into the park slightly there, the view is improved by the spillway being grassed over. So yeah, I think that's all I was going to say about the environmental impact assessment. So I'll hand you over to Anthea to talk a little bit more about the design.
Just managed to unmute myself. I was a design lead at Arup for the project. So I'll take you through just touching on some of the aspects of the design, some of the interesting aspects that we've sort of dealt with. So as Abby's shown, this is the final sort of outline design for the project. It's located at the left-hand side of the dam. There's a side channel spillway sort of embedded in the side of the reservoir. It's dumped into Tumble Bay. It then wraps round through the dam crest and then comes down as a tapered tube, running down the mitre of the dam, and then dropping into a filling basin at the bottom, which, as you'll see from the visualizations and the previous slides, it's embedded back into the hillside. So what I'll do, I'll talk through a bit of the hydrology we looked at, some of the hydraulics, how we approach the access, and then a couple of the little innovative things we did through detailed design. So firstly, the hydrology, the catchment's got quite a high proportion of host class 4 soils in it. So they are designated, they have like reported as having a standard percentage runoff value of about 2%. from some of the papers from the British Dam Society, and from knowledge of some of the people we know in like some of the water companies, it's sort of reported that this value can be actually a bit too low. It could actually be as high as 25%. So you obviously get a lot more runoff than what the host class 4 is giving you. Luckily, we got some gauge data off the Canal River Trust, and we used that gauge data to do our own analysis, and that confirmed that actually that SPR value should be about 25%. So we used that and fed that into our hydrology estimates that went into the flood study. The other thing to mention through the hydrology is the snow melt. So during the design stage in February 2022, the guidance on snow melt and how you apply snow melt was reconfirmed by the Environment Agency, and some guidance was provided to all the panel engineers as to how to apply the guidance. So the methodology that's used is Huff and Hollis. So we used that. Actually doing the revised analysis changed the critical event from the summer PMF to the winter PMF. And that slightly altered the predicted outflow from the reservoir. But through our analysis, that it showed that actually the resulting still water flood levels were still within our design margins we'd used up to that point. So we were okay, but yeah, we had to revise it with updated guidance as we went through. We also mentioned about the downstream flood risk. So originally with our design, we were aiming to obviously pass the design flood and the safety check flood. When we were refining our weir layout, we looked at not just the safety check flood, which is the probable maximum flood, but we also checked it for a 10% uplift and a 20% uplift. So this was in agreement with the QCE, with Martin Hewitt. Instead of applying climate change and other sort of risks to it, we decided to do it as a percentage uplift instead. So that covered any eventuality, so climate change as well as changes in methodology, updated flows, that kind of thing. And that was what we agreed to do, so that's what we did. So we were tasked with reducing the performance of the proposed weir in lower return periods, because we needed to make sure that in those lower return periods we didn't increase the downstream flood risk. Then during planning, we needed to we had some feedback that the Environment Agency wanted us to ensure there was no increase in flood flows across all return periods. So right from the very lowest return period, like the 1 and 2, 1 and 5, all the way up through to the PMF. So we went back and we did a bit more optioneering because of the layout of the side channel spillway in the Tumble Bay and the site constraints that we've obviously mentioned already. We couldn't really increase that structure or change that structure. So we couldn't increase the weir length. So we did quite a lot of optioneering of it's a two-stage weir, of playing with the two levels of the two-stage weir and altering the lengths of them and refining that so that we could comply with the updated planning requirement, which we managed to do. Moving on to the hydraulics, I've already mentioned the two-stage weir. So this is balancing being able to pass the higher flood flows on our design events and ensuring that there's no increase in flood risk in the lower events. So this image on here is showing the top end of the spillway chute. So this is our curved weir shape dropping into the Tumble Bay. So the Tumble Bay, it's got a very high back wall on it, and it's there to dissipate the energy from coming over the weir. As the water has to turn through 90 degrees to get down the chute. So that reduces the water to a subcritical flow. And then we can pass that safely then through the dam crest and around the bend that you can see on the image. Keeping it subcritical means that we're minimizing super elevation on the outside of the bend and any cross waves or any, occurring. And then once it's around the bend, we then steepen it back down the chute. So we've done a step chute. So the central section of the chute is actually a series of steps with smooth walkways on each side. And the step chute then increased the aeration and energy dissipation as it went down the chute. The issue with this is then you end up with a greater flow depth, but actually it was within the boundaries that we could manage within the design. So at the other end of the chute, we then have our stilling basin. So as I've said before, we used a type 3 stilling basin. So these have, as the water drops down to the stilling basin, they have a series of chute blocks at the entrance to the stilling basin, and then they have a series of dissipation blocks in the middle of the stilling basin, and with an end sill at the end. And the idea of these is to slow the flow and to develop a conjugate depth that the hydraulic jump can form in, and you get a nice stable hydraulic jump. When we did the analysis for the stilling basin, because we couldn't guarantee what the River Goyt was doing, whether it was in flood or how much flood, we couldn't guarantee the tailwater conditions. So we needed to have the end sill on the type 3 stilling basin to make sure we got that conjugate depth. When we did our initial analysis, the end sill on the basin would have to be at least 2 meters high. We felt that this would end up with like an unsociable space. Obviously it's emptying, it's finishing in the park. You can see it's right by the children's play equipment. And people use the park a lot. It's a really popular space. So we were concerned that people would climb over the wall and the stilling basin would become a bit of an unsociable space. So we made the design decision to have an open-ended basin and did a bit of optioneering to work out how we could throttle the flows as they left the stilling basin to still get that conjugate depth. And as you can see from the picture, what we've done is we've designed a couple of turrets at the end of the stilling basin that act as a flume, and these provide the depth in the stilling basin to get the hydraulic jump. The other thing that we did some physical modelling, which I'll show you some images on the next slide. But as the chute drops into the stilling basin, we actually found we didn't need the chute blocks because the stepped chute coming down to the basin dissipated enough energy. So we had a physical model built of the weir, the chute and the stilling basin so that we could test the scenarios right from 10 QMEX all the way up to the PMF. So, and we also tested past the PMF to the PMF plus 10% and 20%. And then before we finished with the model, we actually got CRM to run it as high as they could with the pumps. So we got to closer to sort of 30% just to see if the weir drowned out or to see what happened at the very, very high events. And it all still operated really, really well. So the physical modelling proved that our calculations were really effective. We've got really good stilling in the tumble bay. You can see on the image on the left, that's the tumble bay. You can see the weir curved around the top of the picture. And then the chute, so the chute's on the right, the picture on the right hand side. And if you look to the top of the chute, you can see a bit of bubbling in the water. So that's the aeration on the step section of the chute, which is taking out the energy. And then down at the bottom, just before the hydraulic jump, the chute steepens down a steep step section, which gives you additional energy dissipation before we got into the stilling basin. And you can see in the image at the middle at the bottom, the turrets, I think that's at the PMF plus 10%, maybe that image, but you can see the turrets throttling the flow and producing that conjugate depth. Some of the details of the hydrology and the hydraulic modelling that we did. Moving on to the access, post Toddbrook, as Alistair mentioned earlier on, there was a couple of investigations done. So there's the Barnforth recommendations came out of the first Part A study that was done, and a couple of the recommendations that David Barnforth made were that inspecting engineers and supervising engineers need to be able to inspect the spillways closely and to have direct access during their visits, and that the owner should make the necessary preparations in advance to make sure that those close inspections can take place and that it's a routine thing. So we felt that obviously the spillway chute has got a series of movement joints in it, and we felt that the supervising engineer and inspecting engineers in the future needed to be able to access safely along both sides of the spillway, and to ensure that could happen as a matter of routine, we, as Alistair mentioned, the bywash channel has to runs through continually. We throttled the bywash, we contained the bywash channel into a central step channel, and we've got wide walkways on both sides where the inspecting engineer and supervising engineer can walk up and inspect the walls and inspect the base, and inspect every joint. When you need to do a full inspection, we can actually switch off the bywash up at the inlet that Alistair shown right at the start of the presentation, and the whole thing drains out, and you've got a full dry tumble bay, chute and stilling basin to be able to inspect. We also consider maintenance access. Obviously the stilling basin is going to attract silt, debris, and that's where it's all going to congregate and build up. So we, through talking to CRT and the equipment they'd want to use to do the routine maintenance, we've actually designed the exit from the stilling basin to be able to get the required equipment into the stilling basin to be able to clean it and take any debris and silt out. So as far as the Barnforth recommendations are concerned, we have to design for safe access for inspection, but the spillway is obviously also in a very public open space. We had to make the decision as to whether we how we approach access by the public as well. So at the moment, the public use the area in front of the existing weir as a beach during the summer months. So when the reservoir's drawn down to keep the canal system running, people sit on the beach. There's children playing the bywash channel and splash about in the bywash channel. And there's obviously children playing in the watercourse as it runs through the park. So we had to make a decision as to whether we restricted access or whether we accepted access. So if you're going to restrict access and restrict the public getting into this space, we felt we'd have to have very high security fencing all the way around. This would be potential issues with debris blocking, especially across the end of the stilling basin where it discharges into the park. And there was a concern that if somebody did get into the spillway, then they'd have trouble getting out because we put all these big security fences around it. If we accept public access into the space, obviously we get an ease of escape because there's easy access and egress through the structure. There's ease of maintenance, like we've mentioned before, but then there's issues with people hurting themselves, slips, trips, falls. So we decided to make it accessible for everyone, but to discourage access. So make it safe, but make it but accept it will happen. Yes. So sorry. I'll take you through the weir in the tumble bay. We've got across the weir, we actually stepped the weir profile, so you can actually walk over the weir and down into the tumble bay. But it also means if you get trapped in the tumble bay, you can get out. There's also maintenance access, as you can see here, to the top of the tumble bay. So if you get trapped on the far side of the bywash channel, you can get up the back side of it. And the bywash, as I mentioned before, is collected in a low flow channel so that the whole area isn't wet and slippy, but there's a central flow going through. Yeah. So the other thing we needed to consider was the time of flow rise in the chute and the velocity. So if the spillway was going to start to operate and the weir was going to start to operate and someone's in the spillway and they see water starting to build up, how quickly will that water build up and how fast will it be flowing? Will people have time to react and to get out of the space safely? So we did quite a bit of analysis on that to make sure we were comfortable that people could exit safely. At the downstream end, as I mentioned before, the chute's got wide walkways with this step channel in the middle. And the stilling basin is set, and the stilling basin's got these turrets, and it's open to the public, so the public can see into the basin. There's no unsociable corners. But in our final design, we actually flooded the basin to a very shallow depth of about 300 mil. To, like I said, to try to make it safe for people still, but to try to make it something they had to consciously decide to wade through to get to the spillway. And at the time when we were doing our design, the QCE for the project said that if he'd been younger and there'd been a smooth chute with water running down it, he'd have been down it on his rubber tire. So there's another reason why we stepped it, to kind of prevent people using it as a bit of a water park. I go to the next slide. If I just take you through a few of the through the detailed design, a couple of the little innovative things we did and the things we had to consider. When you look at a dam and the safety of a dam, when you do a Section 10 report, you have to consider its seismic performance, and the seismic performance is, and each dam is sat in a different category. So you do the analysis, it sits in a category. So the Toddbrook Reservoir sits between Category 3 and Category 4, which are quite high categories within the UK. So that's because it's quite a high consequence dam, and it's got quite steep side slopes. So by doing this check during the Section 10, the inspecting engineer felt that it needed a bit more of a detailed seismic analysis, and he wanted us to consider both the 10,000-year event and the 30,000-year event return periods. We did this as a staged approach, so we started just doing a pseudostatic analysis within the slope stability and software, and this indicated quite a low factor of safety. So we moved on to a more detailed analysis using FLAC, which is more of a finite element process. And this determined the relative movement of the dam during these events. And it indicated that there could be significant settlement during these events, which would take the crest of the dam below the freeboard allowance and then would allow the dam to overtop. So what we did then, we went out and did some further GI, we did some geophysical survey, and we developed a stress deformation model. So we used FLAC again, but we used PM4 sand as a associated model, and this looked at the liquefaction potential of the materials in the dam. Through all that process, we found that it indicated that the dam, you'll see from the images here, there's the odd little red spot. So it indicated there's very isolated areas that were susceptible to liquefaction at the highest event we looked at the 30,000-year event, which was a very extreme event, but it wasn't sufficient to cause extensive settlement of the crest, and it was a much less than the freeboard available. So we felt the dam was actually safe as it was, and it didn't need any remedial work doing during the design. We also, if you think about the tumble bay is a very deep hole. So we needed to consider the flotation risks of that when it's not full of water. And usually when we do spillway designs, you thicken the base and use it as anti-flotation concrete. When we looked at that for Toddbrook, because it's such a deep tumble bay, we found we needed over 6,000 cubic metres of concrete, with also the associated excavation and the disposal of the material. And it had quite a large impact on the construction period as well, which is quite tight. So we looked at some alternatives. We looked at putting a heel on the structure. We looked at putting a drainage system in, but the drainage system would need to be reliable over the full design life. It would need to be a passive solution, ideally very minimal maintenance. We felt neither of these were particularly suitable, so we looked at tension pile solution. So this is a series of tension piles on the grid. And we found that this worked and provided significant savings. So through doing this, the costs reduced, well, the savings are about 3 million just for losing that amount of concrete. Obviously the environmental and sustainable benefits as well. Another innovative thing we've done is we've considered when the contractor is building that tumble bay, they need to put a ring of sheet piles around it to support that excavation, that very deep excavation. So we looked at incorporating those temporary sheet piles into the permanent solution. So that also aids in reducing the uplift, and it also reduces the concrete volumes brought to site. So looking at including the composite wall design, we looked at saved about £1 million on the scheme, and reduced the programme again. Finally, I'm just going to talk a little bit about the construction flood management. Obviously, we need to manage the risk during construction of flood flows, and we needed to carefully consider the sequencing of the construction. So at the water level management, at the moment, the pumps are still sat in the reservoir basin, and the water level's lowered quite significantly so that it can store the 10,000-year event before the auxiliary weir would operate. As Alistair's mentioned before, we have to keep the bywash running all the time. So we're diverting the bywash channel around the outside of the works while constructing the works. So from this, from the picture on the screen there, you can see the bywash channel would divert around the works, and then we construct sections 3 and 4 first on that figure, and then we can then divert the bywash flows into section 3, and it would run through the lower part of the chute and the stilling basin. Sequencing of the works, the tumble bay was going to take the longest time to construct, so the tumble bay is being started first, so that's section 1. But the idea is we're leaving out the back wall of the tumble bay at lower level, so that if the reservoir fills and the weir operates, it will flow out the back of the tumble bay into the existing bywash and around. And then the works will start at number 4, which is the stilling basin, and work their way back up the chute, and then join together at number 2, so that the period of time that the dam is at its highest risk when we cut through the crest and the core would be like a very short period. The other concern is the auxiliary spillway, because we're doing works to remediate the emergency works that were done at the auxiliary spillway, and to take out the bulk bags and to reinstate it, as Abby showed on some of the planning drawings, as a grassed slope. We found that actually, when you look at the stability of the dam, if you take out the bulk bags and the water level rises in the reservoir, then we had a bit of concern about the stability of the dam at those higher water levels. So there's a bit of sequencing where we don't build the weir in the tumble bay, we keep it at low level, and this ensures that if we get a PMF event, the flood rise won't rise too far, and the dam will still stay stable during those works. So then we complete the works on the auxiliary weir, and then we return back to number 1 where the tumble bay is, and build the weir last. The final thing we need to consider is refilling of the reservoir. So if anyone knows about matters of interest, safety and dam engineering, there's an enforcement date that the Canal River Trust need to meet with their safety works. And the panel engineer has indicated that he wants the refilling of the reservoir to be within that window as well, because the dam's been empty a long time and we need to refill this dam really slowly, and we need to monitor how it reacts. On top of the works we're doing, we're also installing some thermal monitoring on the downstream face that will help monitor the performance of the dam as it refills at the end of the construction period. I'll just pass back over to Alison now for him to go through a few of the construction photos.
Thanks, Anthea. Right, appreciate it. Gone 6 o'clock, so I will keep this section brief. So yeah, very quickly, we're currently on with the enabling works on site at the moment. So one of the key part of the works is moving some existing drainage sort of out the way of the spillway footprint to allow for the tension piles in under the stilling basin. Interestingly, just in answer to Mike Summergill's question, effectively one of the shafts is connecting into part of the drainage system that was installed as part of those 1980s works. And yes, there was some grouting undertaken at the reservoir as well. Lots of Halcro's photos from the time were very useful. We still have them on file. So yeah, effectively we're intersecting some existing drainage at the dam and taking around the spillway footprint. So if we go on to the next slide, please, Anthea or Abby, either one. In order to achieve this, we're basically having to take it round the footprint of the dam. So approximate alignment on site is shown by the red arrows. So we've got 2 large sunken shafts in between the first red arrow, and then some directional drilling in between those, and then that takes us on to basically a more standard open trench construction for the drainage, where it then connects into final drainage, sort of the original drainage system below the site cabins. Interestingly, this is taken from our lower site camera, so we do have time lapse at both the top and bottom ends of the site. So I do believe we're allowed to share those. They are available to the public, so if people are interested, we can share those links so people can watch the construction as it continues on. So click to the next slide, please, up here. This is just a quick look down into some of the shafts. So this one's on the left is shaft 502. It is circa, what's the diameter again? I completely forgot. I think it's about 4.5 meters in diameter. It's approximately 8 meters deep. And you can just see here, that's the directional drilling rig. So what they're doing in that photo is inserting steel liners, coring through to the downstream shaft at 503 on the right hand side there. You can just actually see it's broken through in that image. And then those steel sections of pipe get lined with a UV liner to give us our completed design. Next slide up here. And then the other big shaft we sunk is shaft 501. So this is, sort of circa before the anti-flotation concrete went into the bottom. It was nearly 14 meters deep. It's got about 3.5 meters of concrete in the bottom. And they're a very traditional form of construction to take us into the original drainage system of a timber heading. And sort of people going down there and actually digging it out by hand. So that was an interesting design to review when it came across your desk. Never thought that was something I'd be looking at as part of a project on a reservoir. Next one, Anthea. So the other job that's going on at the moment is effectively all of the piling up at the tumble bay. So we've gone along effectively the back wall, which is the top of the screen, and you can sort of make it out as a rough, faint, zigzag red line. So that section also through the dam core, and this is primarily all piling that forms both the temporary works and permanent works. So the design is there for the excavation, but also then forms the tension face of the composite wall that Arup have designed for us as our sort of effort to reduce the amount of concrete that we're using on site and need for, you know, wasteful sort of temporary works piling that then we wouldn't be using in the long term. So next slide. So this is just a slide showing some of the kit that we've got on site. So that's the leader rig on the left-hand side and also in the foreground of the picture on the right. Just for sort of size comparison, this is going to be about half the size of the rig we've got coming in to put in all the CFA piles for the tension piles. And then if we click to the next slide, these are just some sort of pictures of the progress of the work from our top-end camera. So this is from about 3 weeks ago now. So they've done the initial piling through the core and sort of round the corner, so you can start to see the spillway shape forming there. And in the background, just sort of you can see the leader rig just starting the back end of the tumble bay. We'll click onto the next picture. This is about a week and a half ago. So you start to see the leader rig has got quite a bit of the way down that pile line at the back. And then next photo, please, Anthea. And then effectively they made the turn at the top, so you can get an idea of the length of the tumble bay. And now on site, they basically sort of started coming back along on the weir side. And you can also see in the foreground on the left-hand side of the picture that now they're starting to construct the piling mat for basically continuing on the piling down through the tumble bay, down through the spillway chute, and also the tension piles that need to go in that area. And that is where we are up to date. So I think last couple of slides, one more, Anthea. Yes. So little sort of put it in perspective, the size of the piles we're putting in. So this is my team on the right hand side. So we have an internal design team at the trust sort of working on our smaller work. So we had a team day to get them outside to have a look around. So how long do people think our temporary and permanent works piles are in a standard trust engineer? I'll let you put your guesses in the chat. And yeah, final slide, Anthea. There's your answer, 6. And that is it. So thank you very much, everybody, for listening.
Thank you, Alistair, Abby, and Anthea. I'll be remiss if I don't make an A-team reference there. So I got away with it just then. Really informative and interesting discussion. Thank you also to the South North Wales and Northwestern and North Wales branch for organizing this. We do have a few questions from the audience, so hopefully you can stick around for that. I'm going to combine 2 of them from Mike Summersgill and Paul Bingham about the clay core. So Mike recalls back in the 1980s that there was some investigations to route up the failing or missing clay core of Coombs Reservoir, and was interested in understanding if there was any remedial works that were a result of that in the 1980s. And Paul Bingham also asks, for being drawn out for so long, are there any concerns with the clay core drying out, and what monitoring will be in place? Feel free to take that. Anyone in the group?
Shall I cover the 80s part? Okay, so yes, Mike, following the investigations at Toddbrook, yes, there was some grouting works undertaken at Toddbrook, and also part of that was, I don't know whether you remember, there was investigation works around the original bypass channel of the from the original construction period. So there was grouting works of that, which is part of the local drainage diversions we're doing at the moment. Is we still monitor those structures through V-notches. So we needed to be able to basically pick up those to ensure that should we start getting seepage in the future through them, we can still record those flows coming out. So yes, those works did go ahead, and we've got quite a lot of pictures still on our archives from the time, which provided a very useful record for the works we're doing now. I'll hand over to Anthea for the bit on the clay core.
We through the GI, we determined the clay core is a little bit low and are varying. So as part of the works, we are actually standardising the clay core and raising it along the length of the dam as well. With respect to the risk of the clay core drying out, that's why I mentioned about us refilling the reservoir very slowly and having increased monitoring with the temperature probes on the downstream face. We're doing it, yeah, as a very staged, slow approach at the end of the construction period, just to check that the dam is okay and give it a chance to react and to recover as the water level comes up. So that's how we're managing that.
Great, thank you. And a question from Shailendra. What stage does auxiliary spillage activate in terms of storm return period and the likely impact in the downstream catchment? What residual flood mitigation proposals were considered?
I'm looking at you again, Anthea.
Okay. At the moment, with the reservoir nearly empty, the auxiliary spillway, as Alistair showed, the emergency works, the big concrete beam that was put across. So that's there, so that auxiliary spillway doesn't operate until after the 10,000 year event, which is the design event for a category A dam, which is the dams that within sort of that have lots of community downstream and lots of receptors downstream. So it's in a very safe position at the moment.
Great, thank you. And we have another question. Do you plan to reuse any of the materials from the existing spillway on site after demolition?
So yeah, we are working with Kier, our contractor, to see if we can turn it into a suitable material for the existing spillway and bypass channel that will be made redundant once the new spillway is complete. Needs to be backfilled with a free draining granular material. So we are hoping that we can crush that into that suitable free draining granular material and reuse it on site there. So we'd like to minimise waste off site as much as possible.
Great. A couple more questions, and then I think we might need to wrap up. So one from Trevor. What material is used for the temporary piles?
Standard steel, unfortunately, so nothing fancy.
And one final question. How did you protect the feeder pipes to the canal?
So part of the works that we also need to do, but it will sort of come in sort of the next phase after the enabling works, is the feeder pipes effectively from the end of the existing draw-off tunnels. They will be getting sort of rebuilt, combined into a single feeder. We're only going to use our lower feeder culvert down to the canal, so we still have the two pipes from the dam, but they're going to be joined together, taken under the new spillway structure in some double encapsulation from memory from the drawings, so just to ensure there's no risk of leakage underneath the structure. And we're going to have a new combined operating point downstream. We've also got to put some inlet control on, so we've got double isolation, and the one real benefit from an operational point of view is currently our operating point for our two control valves are within a confined space, whereas this will be moving it out into the open, where we can then send anybody from our operational team who is in confined space trained to go and supply water to our canal network in the future.
Great, thank you. I think that concludes our talks for today. I appreciate all of you, Anthea, Abby, and Alistair, for speaking, and again to the branch for organizing this event. We will post the recording of this to our YouTube channel. Otherwise, we look forward to seeing you at a future SIWAM event.
Thank you, everybody.
Bye bye. Thank you.
Thank you, everyone.